All right, so after this lesson, we're going to have an exam that is the Unit 2A exam, and we have a bookwork associated with this lesson up here. The goal is to learn how projectiles move, and I want you to pause the video, read these questions, and come up with your own answers. And when you come back, I'll have my own answers to share. All right, so my explanations for these is that the child is producing the flight patterns to the right of this question because, first of all, he's dropping the ball, which is the same thing as saying that VI is 0. The second thing is that he's tossing the ball up in the air and then it's coming back down, but that means that it's starting with a VI that's positive meaning up. And lastly, he's both tossing the ball up and out. So it's going to the right as well as going up and down. So that means that VIX, or the initial speed in the horizontal direction, is positive. And also the initial speed in the vertical direction is also positive. A projectile is an object that has both vertical and horizontal speed and is technically in free fall. So I guess it wouldn't apply to a bird or something since the bird is flying and it's not technically in free fall. But it would account for, let's say, a cannonball or any object that doesn't have powered flight, because those objects they're technically in free fall since they don't have any force that's pushing them up or down other than gravity. So if you're an object and the force that you're feeling, the main force you're feeling is gravity, then you're in free fall. And then lastly, it's what's represented by this dotted line, and that would be the path that the object would take if there were no gravity. So because the object's in free fall, it takes this path right here, the parabolic path, but this is the flight path it would take if there were no gravity and it weren't in free fall. So imagine that you're in an airplane and you are moving forward with a speed of 80 kilometers an hour, but there is a wind that is blowing from left to right, or I guess west to east, and that wind is blowing at a speed of 60 kilometers an hour. Then you, in this plane, you're going to be moving both forward at 80 kilometers an hour and eastward at 60 kilometers an hour because the wind will be blowing you. So if you want to know your overall velocity, you have to combine these two horizontal and vertical components into a single resultant that follows this path. And after doing a little bit of math using the Pythagorean theorem, you would find that that resultant speed is 100 kilometers an hour. So we can use that idea in this question right here. A football player kicks a ball with an initial velocity of 25 meters per second at an angle of 53. What's the vertical component of the initial velocity of the ball? I'm going to provide a sketch right now. So there's my sketch. The question does ask for the vertical component of the initial velocity. So we are looking for that component, which is AY. I always give the same advice for questions like this, which is to use the equation that the reference table gives you. It says AY equals A sine theta, and you'll find it right there on the back page of your reference table. It's really lovely for its simplicity. And AY is A sine theta. A is 25, and then sine of 53. Pause the video and solve it yourself before you see my own answer. I got a value of 19.96, I think, but after rounding and significant digits, I got 20. All right, so if you project a cannonball, let's say, at an angle above the horizontal, and it takes a path like this, one of the things that you're expected to know is that if you ignore the horizontal part of the motion, the left and right part, and just look at the vertical part of the motion, which I guess I would motion here, that it actually is following the same path that an object in free fall would take. So, assuming that it were starting up here it would go down, it would have a modest start to its speed, then it would pick up speed, and then it would pick up more speed in the last part of its fall. But it also has horizontal velocity, and the horizontal velocity is going to remain constant over the course of that time period, whereas this is increasing as a result of vertical acceleration. So I just made note of that the vertical speed is increasing, and that's going to be as a result of a downward force, which is the force of gravity on the object, so it's causing acceleration downward. But the horizontal speed is constant precisely because there is no force in the x direction. So there's no Fx. And if there's no force in the x direction, there can't be an acceleration. So no Fx, no acceleration. If there is a force going down, if there is a downward force Fg, then there is going to be a downward acceleration. You must know from this slide that the two components of the object's motion are independent. And that just means that we can use a certain set of equations on this object's motion, and they'll be sort of free fall equations that include acceleration, such as, for instance, d equals vit plus 1/2 at squared. But for this object, at least for the horizontal part of its motion, we're going to use simple equations like v bar is d over t because it avoids acceleration. So again, there's no acceleration in the x-axis, so we can use a simple equation with no acceleration. But in the y-axis, we do have acceleration. It's independent of the x-axis. And so we'll use equations that have a. Other examples of equations we might use are vf squared equals vi squared plus 2ad, and vf equals vi plus at. This is just an example right here. So in this slide, what I intend for you to notice is that there are two ball A and B, and they are taking different flight paths, but there is a part of their flights which is the same. So B has been given a horizontal velocity as well as being allowed to fall. So it is moving to the right at the same time that it's moving down. But A is not given any initial horizontal velocity, it's just falling. But one thing you can notice is that at every time interval, the location of ball A and ball B actually match up. So I think I just covered that right there. The reason for that matchup is because they receive the same downward force and they would get the same downward acceleration and would have the same speed at every point. So I just highlighted those points here. If they have the same downward force, the same gravitational force, then they have the same acceleration and the same speed. And the horizontal part of the velocity is the only thing that differs. But I will point out one more thing on this slide, which is that the horizontal component of the second ball is rather consistent. So I'm just drawing in blue lines to mark its horizontal displacement at each of these time intervals. And you'll notice that the blue lines are equally spaced. That indicates that there is no acceleration. And the reason why there's no acceleration is because there is no force in the x direction. So both of those logical trains, these two that I just circled in black, they explain different things. The first one over here on the left explains why balls A and B have the same vertical speed, and this one explains why ball B has a constant horizontal speed. So I just labeled those y vx is constant and y vy's are identical. So in this question, I just say that if still two balls, we have one being dropped and one being dropped as well as pushed out. Two different diagrams, same thing. But if one ball were thrown horizontally at 10 meters per second from a height of 44 meters above level ground, and a second ball were dropped from the same height, which would hit the ground first? So these two diagrams are illustrating perfectly what the question is saying. One ball is simply dropped, the other one is tossed horizontally. And the question is, which would hit the ground first? Think about an answer, pause the video, and then come back. And my answer is firstly that the vertical and horizontal motions are independent. So this horizontal speed right here, where it says thrown horizontally at 10 meters per second, is not going to have any effect on the ball's drop. So when it says it's dropped from the same height and which one would hit the ground first, this stuff won't affect which one would hit the ground first. And then secondly, just know that they have the same gravitational force, so that means they'll have the same acceleration, and they'll also have the same vertical speed. So on this slide, we're just going to go into a little more detail about what's happening during these flights. So if you remember from the last slide where the ball, there was one ball being dropped and there was one ball being sort of kicked out to the side, and it was falling as well. The one thing that you could notice was that in every 1 second interval, the ball was traveling the same horizontal distance. So as it moved to the right, while it was falling, it was covering, I think, exactly 10 meters in every 1 second interval. If the ball had been traveling with a greater horizontal velocity when it first started, so if it was given a harder horizontal force, giving it a greater horizontal velocity to start with, then it would have had a much larger displacement. So in the two diagrams that follow, I am giving you a question about whether if the balls had been launched with the same initial velocity but at different angles, why do the flight paths differ? So that you can tell that the velocity is the same between the two. It's this vector right here, because if you compare the length of this vector to the length of that vector, you'll see that they're the same length. So they're given the same initial velocity. It's just that they have different flight paths because they're launched at different angles above the horizontal. So the goal is to explain why that happens. So pause the video and think about it, and then I'll share what I think. So we've discussed this piece before in a previous lecture, but when the angle theta is lower, it's going to accentuate AX component of the triangle, but when angle theta is higher, it's going to accentuate the AY component of the vector. So here's a sample problem. You have a plane flying horizontally at an altitude of 490, and it has a velocity of 250 east, and it drops a supply packet to a work crew on the ground. It falls freely with no parachute, assume no wind resistance, and negligible air resistance. Calculate the time required for the packet to hit the ground, and calculate the horizontal distance from the target area that the plane must drop the packet. So these are two different questions. I guess we'll call them A and B. And A is unique because it's asking about the time required for the packet to hit the ground. And this is purely a vertical question. I'm saying this because I want to highlight again that the vertical and the horizontal motions are independent of one another. So the vertical motion is going to be governed completely by equations that involve an acceleration of 9.81. So I think that's like the most important thing to remember here, is that if you can determine that the question is about like only vertical stuff, so like calculate the time required for the packet to hit the ground, that's just involving it falling from 490 meters. That's all vertical, and that means that it's a free fall question. So free fall questions, you just think of them as completely vertical, and you only use an acceleration of 9.81. I'm going to go back and label all the pieces in the question just to make sure we have everything. So when it says a plane flying horizontally at an altitude of 490 meters, that would be a distance. And it has a velocity of 250 per second east. So I'll say that is VI, that's initial velocity. It drops a supply packet to our work crew on the ground if it falls freely without a parachute. Okay, so that's really all we have. We also have an acceleration of 9.81. So one equation we can use for this one is d equals VIT plus 1/2 AT squared. And the reason why we can use that is because this section is going to fall out. It's going to be 0. And the reason for that is that the initial velocity in the vertical direction, or VIY, was 0 meters per second. That means that it was moving horizontally, but it wasn't falling yet. So vertically, it didn't have any velocity. So at this point, I'm going to rearrange it so that I can solve for t. So I'll circle t. So starting from here, all I've done is I just rewrote it without VIT in the equation, and I am going to divide both sides by 1/2 a, and that will at least get t squared alone. So then I'll know that t squared is d over 1/2 a. And then we'll need to do the square root of both sides. And then I'll have t equals the square root of d over 1/2 a. And then I can plug in. The distance that it's falling is 490 meters. And we have 1/2. And the acceleration is 9.81. So go ahead and press pause and solve that now. So I got 9.99 seconds, and with significant figures, I think I'm only going to get to keep 2 of those. So I would just round that to 10 seconds. All right, so part B. It says to calculate the horizontal distance from the target area that the plane must drop the packet. So basically, since the plane is going to drop the packet, let's say right here, and the packet's going to continue moving with the plane. It's going to follow this path that you've seen before with projectiles. So when it hits the ground down here, it'll be some distance x ahead of where it was actually dropped. So it would have been dropped like down here, and then we have this distance x that it's going to move through before it hits the ground. So that's going to be the distance that we're going to solve for. Basically, we just need to figure out how far the package is going to move in the time that it takes for it to fall this way. So I'm going to do a really simple equation for this. I'm just going to use v bar equals d over t. And this equation doesn't have acceleration in it. And I'm choosing it on purpose because in the horizontal direction, there is no acceleration. This object is going to moving from left to right, it's going to be moving at constant speed because there's no force on it in the left to right direction, in the horizontal direction. So no force means no acceleration, and that just basically means constant speed, and I can choose an equation that has no acceleration in it. So v bar is d over t, and then that would mean that d is v bar times t, and the v bar is 250 meters per second east. So I'll toss that in. And the t is the amount of time that the packet is spending in the air. And the amount of time the packet spends in the air is determined by its fall. I'm going to actually use this number, the 10 seconds that I just solved for. So it was in the air for 10 seconds, which means that the distance that it is going to fall through in the horizontal direction is going to be 2,500 meters. So now that we're in the habit of talking about the components of velocities, let's do a different question with a different sort of flavor. We have this vector that's representing the initial velocity, that's VI, of in this question, it's going to be a golf ball. So we have the initial velocity of the golf ball going up like this. But that velocity can be split into two components, a horizontal component, which we'll call VIX, and a vertical component, which we'll call VIY. So this question asks me to solve for the horizontal and the vertical components of the velocity if the initial velocity is 50 meters per second at an angle of 30. So I think the best equations to use here are these equations, which are just adaptations of the same equations that we've been using, which were ax equals a cosine theta, that's this one, and the other one would be ay equals a sine theta, so those are just adaptations. So if I want to have the horizontal and vertical components, I'm just going to write them in, and I will choose values. So vi cosine theta, and let's see, vi is 50, cosine 30, and then I'll just go ahead and do the viy as well. So it's going to be vi sine theta, and then that'll be 50 sine 30. So let's go ahead and solve now. So I calculated them. I got 43 meters per second for the initial speed horizontally, and I got 25 meters per second for the initial speed vertically. All right, so on this slide, the two really important things are that there's this type of question that you're going to get, which is where you have to find the time t that a projectile takes to reach its maximum height. I recommend using this equation, and there are a couple of tips. The first tip is that just know that when the object reaches its maximum height, its value for final velocity will be 0 in the vertical direction. And it's a reference to this idea that at least vertically, when it reaches the top of its flight, it hangs motionless in the air for a moment. And at that point, its vertical speed would be 0. It is worth noting, however, that it's still moving to the right, but its vertical speed is 0. So know that you're allowed to put a 0 for VF when you're solving for the time t that it takes to get to its maximum height. And then my second major point on this slide is that if you're trying to solve for the time it takes for the object to reach this point, then what you could do is you could solve for the time it takes to reach that point. So just use this note right here. So solve for this, but then assume that this part of the flight and this part of the flight are opposites of each other, but equal. So in any case, if you can solve for the time it takes to get to this point, then just multiply that time by 2, and then you'll have the amount of time it takes to get here. Okay, and the last bit, and this one is, I think, vital to these questions, is that at the beginning of the flight, the initial velocity is up. So let's call that positive. And throughout the flight, it is getting a vertical acceleration, but the vertical acceleration is downward, and that's going to be the acceleration due to gravity. So you could think of it as A, but some people will call it G because it's an acceleration due to gravity. But in any case, the really important part is that it's downward, that acceleration, which you can think of as negative. So this is going to be one of the first times this year that you might have to really pay close attention and assign a positive value for the initial velocity, but a negative value for A. It doesn't come up all the time, but when it does come up, it makes the difference between the right answer and the wrong answer. So be aware that the initial velocity has a direction, which could be up, and the acceleration has a direction, which is down in this case. So just know that they would have opposite algebraic signs. One would be positive and the other would be negative. I added in here at the bottom as well that there are occasions when I will use this equation to solve for rise time rather than this equation. But both work in different circumstances, and we can use either one in some cases. On this slide, the major things that I want you to know is that there's an ideal path that projectiles take, which is along this trajectory. We would call that parabolic. And that path is idealized. It's the one that we think using math and physics that it should take. But if you look at projectiles in the air, if they don't have any force after their initial launch, then their actual path is somewhat stunted. It looks something like that, sort of like a wilting flower. And the reason for that is air resistance. So at every moment that the object is flying through the air, there is a force of air resistance, which is pushing backward on the projectile. It's just called air resistance or wind resistance, and it's a kind of friction, but it's going to make the actual path shorter, and so like shorter in the vertical direction, but also shorter in the horizontal direction. So the way I would state that in terms of Regents language is that there's less height and there's less range. So the other thing on this slide that's pretty cool is that depending on the launch angle, like if a ball is launched at an angle of, let's say, 30 degrees, that it will have the same range as another ball which is launched at a complementary angle. Complementary meaning that they add up to 90. So if you're launching one at 30, then expect its range, which is the horizontal direction, expect its range to be the same as a ball who was launched at 60. So I'll follow this one back, and that's the 60-degree one. So 60 and 30 will have the same range. 15 and 75 have the same range because they add up to 90 as well. And of course 45 and 45. So you should know that complementary angles will have the same range. They do have differences in flight time. However, I think it's pretty obvious that the ball that's launched at an angle of 75 degrees would be in the air for a longer amount of time, and it would reach a taller height. But it would only go the same horizontal range as a ball that was at 15 degrees. So I went ahead and added in that complementary angles will give you the same range. And in this question, however, the height and time of flight differ. The reason is because in the ball that's launched at 75 degrees, for instance, most of its initial velocity is vertical, so it's going to have a longer flight time. So I just went ahead and wrote that in. And then lastly, I would say that air resistance is the reason that a real flight path is shorter and lower than an ideal flight path. Okay, so 3 questions here. We'll call them A, B, and C. And they're all about a small missile that's fired with a velocity of 300 meters per second at an angle of 30 above the ground. And after a total flight time of 30.6 seconds, and that's the total time, so that's the time that it takes to both rise and fall. After a total flight time, the missile returns to level ground. And in the first question, it says, calculate the initial horizontal and vertical components of the velocity. I suggest using ax equals a cosine theta and ay equals a sine theta. All right, so there's that. So ax, that's what we're solving for. The value for a is the hypotenuse of this triangle, and it's going to be 300 in this case. And then cosine is the function, and the theta here is going to be 30. And in the second setup, we're solving for ay, which is the vertical component of the initial velocity. You have the same value for a, it's the same hypotenuse, but we're using the sine function in this case and the same theta. So go ahead and solve that and then come back and I'll have the answers. All right, so I got 260 meters per second for the vertical component of the initial velocity and 150 meters per second for the horizontal component of the initial velocity. So part B, calculate the maximum height of the missile above the ground. So if we're going to calculate the maximum height, then I suggest using the equation d equals VIT plus 1/2 AT squared. And we can use the time that was given in the question if we divide it by 2. And the reason for that is because we're only going to solve for the maximum height, which is really just half the flight. You're just going from the bottom to the top of its flight. So it's only half the flight, and the t that they gave us was the total time. So the half of that time would be 15.3 seconds. So I'll use that time in this equation. It's already set up for us, so I'll just go ahead and go through with it right now. The initial velocity that we're referencing right here, that's an initial vertical velocity. It's not the initial velocity. So don't use 300 because 300 is both horizontal and vertical. So we only care about the vertical part of this velocity since this question is essentially a vertical question. It wants to know how high it's going. So I am going to use the initial vertical velocity, which I just solved for, and that is 150 meters per second, and the time is 15.3. You have the fraction 1/2, and the acceleration is going to be negative 9.81. It's really important that it's negative in this case because it's in the opposite direction as the initial speed. And then the t squared is going to be 15.3 squared. So I want you guys to go ahead and solve for this and then come back to see my solution. So I got 2,295 for this section of the equation, and I got 1,148 for the entire part right here. But I changed it from a positive to a negative because remember that the acceleration was negative, so it changes this side of the equation to a negative. And also, I think you can see now the difference between a positive and a negative is going to make the answer very different, and that's all because I remembered to make the acceleration negative here. So the answer I got was 1147. The last question on this slide is looking like it's going to be the easiest because it asked me for the total horizontal range of the missile. And horizontally there's no force, and when there's no force there's no acceleration, which means that you can use an equation like this, which does not include acceleration. And so v bar is d over t, and d is v bar t. The initial speed is going to be the initial horizontal speed, which is 260 meters per second. And that speed is going to be carried throughout the entire horizontal part of the trip because, remember, it's not accelerating, so it's going to be moving at constant speed of 260. And the time that it moves at that speed is, in fact, the total time of flight, or which is 30.6. So you just need to multiply those two numbers together, and you'll get 7,956 meters. And with that, we have reached the end of the lesson. Congratulations. Here is a preview of your pair up and your summary. And you're just scanning them because I'll try to have these copied for you and ready for you when you show up to class tomorrow.